All right, lesson 1.13 through 14, function models and applications. So our skills and learning objectives are to construct models from data set and justify, identify an appropriate function type to construct a function model given a scenario, describe underlying assumptions about a model for a given scenario, construct a linear, polynomial, or piecewise defined function to model a scenario, construct a rational function model based on a context, apply a function model to answer questions about a data set, and use technology to find and compare regression equations. Okay, in part A here, it says this lesson will help us to construct linear, polynomial, and piecewise function models and applications given real-world scenario. So how to identify the type of function. Linear, if it's linear, the output values will always increase or decrease at roughly a constant rate of change. Quadratic, the output values will have a constant second difference, that is, they'll have a linear rate of change, and the data sets will be roughly symmetric with a unique maximum or minimum value. If it's cubic, the geometric context, it'll involve volume or something with 3 dimensions. And then piecewise, it would just be a data set defined over non-lapping domain intervals. All right, so in example 1, so in each data set below, give an explanation to justify why the model fits. All right, so the first thing I'm going to do is I'm going to check my differences. And so I can see that my x's are all increasing by 1s, but my y's, I'm subtracting 4. We have a constant rate of change there. So we can see that as input values increase, the output values decrease at a constant rate. Of 4. Decrease gave us a negative constant rate of 4, which means it is linear. Now, B is the data set models a quadratic function. So again, I'm going to check my differences, but if it's quadratic, then I should have roughly the same second differences. So I can see my x's are each increasing by 1. For my y's, I'm down 10, down 6, down 2, up 2. So here I would be up 4, up 4, up 4. All right, so we can see that second differences are constant. We can see that there is symmetry in the output values. So right here, if we notice the -1, which means this is my vertex. Okay. And so at x is 2 and y is -3, it's a minimum output value. So we can say that, +2, -3 is the vertex, which will be a minimum in this case. All right, example 2. So the data set for our piecewise defined function h is given in the table below. Determine the 2 open intervals where the rates of change are 2 different constants. So it's telling us to look at those rates of change. So our x's are all increasing by 1, so we only have to look at our y's. So here we're increasing by 3, by 3, by 3. Then we're decreasing by 1.5, by 1.5, and again decreasing by 1.5. So we can see that right here is the point at which it's going to overlap, okay? So determine the 2 open intervals. So it's from -3 to 0. So rate of 3. And then we can see from 0 to 3 has a rate of -1.5. All right, B wants us to write the piecewise defined functions that model the data. Now remember, this is the point they shared. That's the y-intercept. That's the b value because these are linear. So we know it's y equals mx plus b, where our rate is our m, and that y-intercept, the -4, is our b. So we're going to have f of, oh, it says function h, so I need to name it h of x. All right, so the first one we can see is 3x minus 4, and that's from -3, to 0. And it doesn't matter which one you put the equal to 0 on, but that was the thing I had a little trouble with here. It's one or the other, but not both when we actually go to do this. So I probably should have up here made that a parenthesis, since I made that one into an equal to. All right, and then my other equation is going to be -1.5x minus 4, and that 0 is less than or equal to x, less than or equal to the 3. Nope, no equal to on the 0. Just talked about that. All right, geometric models. So let's use a graphing utility to draw a scatter plot, then create a line of best fit to analyze the data set. All right, so this is the bad thing, is that I can't show a calculator on here, okay? But it gives us the steps here. So, and also at the very back of your notes, if you flip, I think it's the back of your notes. If not, I need to give it to you. I have my answer key, it has it on it. Let me check. All right, so I did check. So yes, at the very back of your notes, you'll see that you have directions on how to input things into the scatter plot for a TI-84 and a TI Inspire. So those are the only two I have instructions on. And we use the 84s, but it also walks you through it here on 3. So let's go ahead and let's put this data into our calculator. Okay, so we're putting the data in our calculator now. Let's actually go ahead and read through this. It says, let's use a graphing utility to draw a scatter plot, then create a line of best fit to analyze a data set. So I already told you your instructions are included at the end of your notes there. Example 3 says a fresh market price of Florida oranges in dollars per box is shown in the table above. Write the linear regression model for the price of oranges in dollars per box. And so it walks us through it right here. It tells us, first thing we're going to do is enter our data in L1 and L2. And so if you notice, though, in L1, those are your X's. They took and they changed it from 2006. They said that's year 1, year 2, year 3, year 4, year 5, year 6, and year 7, okay? And then they put the Y's, the price per box, in L2. So then you're going to go, so enter that in L1 and L2. If you need to, pause this as you're going through it. Then you're going to go to Stat. I guess I should have told you here. This is Stat Edit. Sorry. Put those in L1, L2. Then you're going to go Stat, go over to Calculate, and you can choose 4 or 8. I'm going to use 4, which is the one that looks like what they have there, y equals ax plus b, and it gives us our a, and it gives us our b value, and we just got to plug them into the equation. All right, now, when you go into your stat calc, choose 4 or 8, it doesn't matter. You'll notice when you go through here, your X list is in L1, your Y list is in L2. Don't worry about the frequency list, but right here where it says, okay, well, I just had a notification thing show up on my iPad, and when I did, it paused the video on me, so I'm not 100% sure where exactly it was, but I know it was right here in this calculator part. So I'm just going to start over on the calculator. So it says to write the linear regression model. So we're going to go to Stat Edit. We're going to put our X's in L1 and our Y's in L2. And remember, I'm pretty sure it was recording at this point. So we changed our years to be year 1, 2, 3, 4, 5, where year 1 is the year 2006. All right, then we're going to go back into Stat, but this time we're going to arrow over to Calc. And we want to run linear regression. So we're going to either select number 4 or number 8. When you do that, it's going to give you a screen that looks like this. Your X's should always be in L1. Your Y should always be in L2. Now, the store regression equation, we want to be lazy. We don't want to have to write out or type in our equation if we need it in y equals. So we're going to store it. So if you go right here on store regression equation, and if you hit alpha trace, it will give you a list of the y's. So just pick y1, which is number 1, and then go down to calculate. When you do that, it should show you this. Okay, so it says our equation is y equals ax plus b, where a is 0.357 and b is 10.389. And so that is going to be our equation. So A said to write the equation. So I'm going to write it right above it here. So it's going to be y equals 0.357x plus 10.389. B says use your linear function to estimate the price of a box of oranges in 2014 and 2015. All right, well in 2014, my x will equal, let's see, 2012 is 7, so 2013 is 8, so that would be what, 9? All right, so we're going to find f of 9. And so we can plug it into the equation, or you stored this in your calculator. So go look at your calculator, and it'll tell you 13.603. So we're talking money, though, because remember, we're talking about the price of oranges. So it's $13.60. Now for 2015, that's the next year. So we know x is 10. So f of 10 is going to be $13.96. All right, another way to check, if you're unsure, now we were lucky, we were like just 2 away, so we were able to count up. But what if we weren't? So you could take the year, so for example, 2015 minus 2006, because that was our first year, that's 9, but you have to include that first year, so you have to add it back in, okay? Because when we subtracted out the 2006, we took the 2006 out as well. So then we have to put that year back in, so we have to add 1 to it. Same thing if we'd have done with 2014. So if you'd have done 2014 minus 2006, that's 8, but you have to add that first year back in, and that's how we get x is 9. All right, example 4. It says the average length of cell phone calls, L, in minutes for a high school student during the second semester, January to June, are shown in the table above. The model is known to be valid for January to September. A quadratic regression, y equals ax squared plus bx plus c, can be used to model this data, where L is the average length of a call and t equals 0 represents January. So they're telling me right there, 0, 1, 2, 3, 4, 5. Okay? Write the equation, the quadratic model for this data. And so they already told me it was quadratic. So I'm going to do the same thing. I'm going to go to Stat Edit. And you might want to clear your calculator because you just put data in it. It's up to you. If not, just delete your data. You can go up on L1 and L2, hit clear, not delete, but hit clear and arrow down, and it'll clear the data for you. All right, so go into your Stat Edit, put this information in it, and pause the video until you get that done. All right, so now that our data is in our calculator, we want to run the regression, so we're going to go to Stat Edit, and you're going to arrow down to quadratic regression, quad reg. Okay, and that should be number 5. All right, so same thing, X list L1, Y list L2, store regression equation, go store that in L1. So alpha trace Y1 and calculate. I think I said L1, I meant Y1. All right, so when we do that, we get our equation. So it's going to be 0.39285x squared minus 0.21285x plus 8.81428. Now it says, use the model from part A. What is the estimate the average length of a cell phone call in July? Well, July will be month 6. So since we put this into our Y1, we can go to our table, go check when X is 6. And so it should tell us that it's 21.68 minutes approximately. All right, writing functions from formulas. Example 5 says a perimeter of a rectangular garden is 84 feet. Express its area as a function of its width, W, of a side. So we know that the perimeter is 84 feet. Well, we know it's rectangular, so remember perimeter is 2L plus 2W. And we know perimeter is 84, which means 2L plus 2W equals 84. Now it says I want to express the area as a function of the width. So remember, area is just length times width. Well, I want it as a function of the width, so that means I need to keep W in it. So I need to substitute out that L. And I need that L to have something with W. So that's where this part 1 equation comes from again. If I solve that for L, then I'll know what the length is equal to, and I can plug that in over there. So let's do that. Let's go back to part 1, and we're going to solve for L. All right, so first thing I notice is everything here is divisible by 2. So that means that L plus W equals 42. Solve for L. L equals 42 minus W. So now if I come up here, I have A equals, we know L is 42 minus W times W. And so I could distribute that, and so my area is equal to 42W minus W squared. So it says express its area as a function of the width. So I've got my area, and as a function of means and the variable is W. So I need W on the other side, which I do have. So there's our answer. All right, domain restrictions. It says a function model may have underlying assumptions about how quantities change together. You might need to consider contextual clues that indicate a need to restrict the domain and or the range for your model. Consider the garden example above. The length of the garden can be no more than 24 feet. What is a reasonable domain and range for this scenario? All right, well, the domain can be no more than 24 feet. I'm sorry, the length can be no more than 24 feet. So that means that it has to be between 0 and 24. Well, it's not going to equal 0, because if it equals 0, I don't have anything. No more than means it can equal 24. Okay? But remember, we know L is 42 minus W. So 0 is less than 42 minus W, less than or equal to 24. And then we can just solve for W. So we'll subtract the 42. So negative 42 less than negative W, less than or equal to negative 18. I believe so. All right, and then divide by negative 1. Now be careful. Remember, when you divide by negative, your signs change. So we get 42 is greater than W, which is greater than or equal to 18. So this means that 18 is less than or equal to W, less than 42. All right, which tells me that when my length is the largest at 24, then my width should be its smallest as 18. So my range then is going to go from 0 is greater than, now remember that the A equals was the equation, so that's my area. So the area is a function of the width. It has to be less than or equal to that area of, we just said it can't be, it's going to be the 18. All right, and so we get 0 is greater than A of W, which then I just go find A of 18. So A of 18 is equal to 42, times 18, plugging it into this equation up here. So 42 times 18 minus 18 squared, and we should get 432. And so there is my range. All right, example 6 says the volume of a right circular cone is V equals 1/3 pi r squared h. If the height is twice the radius, express the volume as a function of the radius r. All right, so we know the height is twice. Height is twice means 2 times the radius. So the height is 2r. Now, A says express the volume as a function of the radius r. So remember, as a function of means, and the variable is r. So the only variable we want up here is to be r. So I need to replace h with 2r. So we got V equals 1/3 pi r squared times h, which is 2r. And so when I multiply this out, I get 1/3 times 2 times pi r squared times r. I just group my like things. So V is equal to 2/3 pi r cubed. Now B says find the volume of a paper snow cone cup whose radius is 2. So now it's saying, hey, my radius is 2. Go tell me what the volume is. So V of 2 equals that 2/3 pi r cubed, but r is 2. All right. So it's what? 2/3 pi times 8. So 16/3 pi, if I want exact, and this would be inches cubed. And if I wanted approximate, I could throw that in my calculator, and it should tell me 16.755 inches cubed. All right, example 7 says the table below shows the height in inches of a transmission fluid that is being drained from a large storage tank. So they gave me a table here. It says model the data with a quadratic function. So we're going to go do our stat edit and run quadratic regression. I'm going to go ahead and store that in my Y1. So either clear your calculator or clear your L1 and your L2. So we're going to put our time in seconds in L1, our height in inches in L2. I'm going to go run my quadratic regression. And so when I do that, pause this if you need to. Here's the equation that I found. All right, B says use the model to estimate the height of the transmission fluid in the tank at 35 seconds. 35 seconds, that is my X. So I know that X equals 35. So I can plug 35 into my equation, or I can go to my table and find H of 35. And it should give you 59.723. And it's the height, so it's measured in inches. And how long will it take to drain the storage tank? Well, to drain the storage tank means that our height is going to be 0. So we need to find where it's going to equal 0. And I can tell you now, it's not going to be a nice, pretty whole number. So you can't just go to your table and find it. So what I would do is your equation is in y1, right? That's what we have that quadratic equation in, my regression. In y2, go put 0. And we want to find where they intersect. Now, we want to know the positive side of where they intersect, not the negative side of it, okay? Because when this is going to be a quadratic, it's positive quadratic, so we know it's opening up like this. And so when we do 0, it's going to cross. And so we want to find where it crosses on the positive side. All right, once you can see where it intersects, go to second, trace, intersect. Go move that cursor on top of the intersection and hit enter 3 times. And so what you should find out is that the time is approximately 87.743 seconds. And that's it for part A.